Welcome to the sixth video in this series. The topic this time is connection to reality. This video would also deserve to be called one of the most interesting lectures, since we will finally learn how to create measurable quantities from these Lagrangians that we discussed so far. We will do this by introducing the S matrix or the scattering matrix, and we are going to go into the details of the interaction picture, and we will develop the Dyson equation. We will ask for some help using the Wick theorem, and finally, we will represent all these theories with diagrams, the so-called Feynman diagrams. After Feynman diagrams, we will discuss cross sections, and then we will go into the details of how these things could be compared to measurements that we do at CERN. So then, let's dive into some collision physics. So how can we check that our theories really describe nature? Well, in particle physics, we usually do collision experiments. We collide particles, and so we should figure out a method that transform these theories that we developed into something that could be measured in a collision experiment. So, we have an incoming particle, and we have another incoming particle, and they collide, and we should somehow figure out how to describe the collision. When we are in the beginning of this story, then the particles are still free, right? So this is the free particle. They are not interacting, no interaction. And so that's easy to describe. It's easy to describe free particles. That's actually kind of what we have been doing in the past videos. But what's interesting is this part. So this is where the interaction happens. And that's hard to solve. And we are looking for a recipe on how to actually solve this part. And so the mathematics that describes this is by the scattering matrix, scattering or S matrix. So that's what actually what we are going to start with. So 6.1 is the S matrix. So when we have the states infinitely far from each other, then they are free. That's what we were discussing. So we could say that we have an initial and a final state of the system. I denote the initial state as I and final state as F. And so without, or in this situation, when we start the collision, that is, we think about it as the limit, and the time is minus infinity. And then also, when the time is at infinity, then this is the situation when the particle is free. And we know we already know how to describe it. For the scattering amplitude, we are interested in the scalar product of the particles, not at the time in minus infinity or infinity, but when the collision happens. So let's say that the collision is at t equals 0. T equals 0 is the time of the collision, and the scattering amplitude is going to be denoted with an A, and it is the scalar product that we have a particle A, like this, at t equals 0, multiplied with the particle B at, again, t equals 0. So now we need to evolve our states from the initial and the final states into this t time. Or let's actually remember that we had this time evolution operator, So the time evolution was described by this U operator. And so let's say that this U operator evolves from T to T0. Actually, the other way around. From T0 to T. And also, if these two things are the same, so if we have the operator for T and T, so we evolve something from the same time to the same time, that's the same as not doing anything, that's the identity operator. Also, we could think about that if we do an evolution from a t1 time to a t2 time, and then we do an evolution from the t2 time to a t3 time, that's essentially the same if we would do an evolution from the t1 time to a t3 time. So we know that the I and the F states were free particles. And so we could say that we want to evolve those into this part and they are interacting. So this curly A was the same as the scalar product of the final situation, final state. And you remember that that final state was in the plus infinity. So what we need to do is that we need to like move that back from infinity to the time t. And then we also have the initial state that we need to, which you remember was at the minus infinity. So we need to also evolve that to this time t from minus infinity, right? So this u acts to the left and this u acts to the right. It moves from minus infinity to t time or 0 time, it doesn't really matter. And then this one acts to the left and moves the situation from t time to infinity. So this describes the whole situation. So if we are going to use this knowledge here, that we can move these two together, then this is the same as writing that the final state, and then we have the U operator, which now is acting, or which is between minus infinity and infinity. And then we have the I initial state. And so this actually is what we call the S matrix. So this we could say that this is the same as the final state S initial state. So we really didn't do much here, just said that we have two states which are free, the initial and the final state, and whatever is in between is actually packaged into this S matrix. So the next step is to figure out what is this S matrix is hiding, and that could be done in several ways. We are going to choose the simplest one, but before that we need to introduce the interaction picture. So 6.2 is going to be the interaction picture. In the third video, we introduced how states and operators evolve. We discussed that in the Schrödinger picture, the operators don't change in time, but the states do, and they do it according to the Schrödinger equation. So we had, let's just denote, the psi t was the state depending on time, and so that we really make it sure that it's obvious that this is in the Schrödinger picture. Let's put an extra s here. And the A operator had no time dependence here in the Schrödinger picture. So this is the Schrödinger picture. And the equation that described the change was the Schrödinger equation. So the I times the derivative of the psi state at t, which I am denoting with this extra s index, was described by the Hamiltonian operator acting on this psi state, and I still have the s here. We also discussed, although we didn't actually name it, that in the Heisenberg picture, the operators evolve and the states are stable. So you remember that we had this A operator, which is time dependent. So let's again to be very obvious and put an extra H here for the Heisenberg picture was described. This was the U dagger AU thing, and then we also figured it out that that can be described with this exponential. So E had I H T, which was the U dagger, and then we had the AS operator, the same as here, and then we had the U, which was the minus I H T, and the states were just called psi H. So this was the Heisenberg picture. So there is a new thing now, which has the mixture of these two, which we call the interaction picture. So in the interaction picture, we usually defactorize the Hamiltonian into two parts. So we say that the Hamiltonian has two parts. One of them is the H0, and the other we call the H prime. So the H0 describes the free behavior, free particle, and this thing is the interacting part. So now let's denote the state often in the interaction picture as the psi t I as for the interaction, and we have the operators as a I t. So now we have a situation in which both of them are time dependent. This is the interaction picture. So now the equations to describe how this change in time are going to be that the psi at time t in the interaction picture is something which we get by using the exponential I h0 and the time acting on the psi at time t in the Schrödinger picture. And the operators A in the interaction picture at time t we get by taking the exponential of I h0 t, this should be an operator, and then we have the A from the Schrödinger picture, and we have the same thing conjugated, so we had minus I h0 operator at time t. So if I want to include an example for this A by inputting the Hamiltonian here. So the Hamiltonian in the interaction picture, depending on the time, just applying this equation, is the same as the exponential of I h0 t, the h is an operator, then I have the h I at the time t, this is the interaction, so there is an extra prime in here, and exponential of minus I h0 t. So I really just plugged in h I prime to the space of the A. The time evolution is described by the Schrödinger equation. So we can still write that I dt of the psi state in the Schrödinger picture is the same as the Hamiltonian operator acting on the psi state. Just wrote the Schrödinger equation again. I did that because I want to rearrange this thing and unplug it. So from this, we can say that the psi ts is the same as the psi ti if I take this exponential to the other side. So from this I can express that psi ts is the same as the minus I a0 operator t times the psi t at the interaction picture. So I really just multiply with the inverse of this, which gave us 1 here, and the, the, the same thing with the minus sign on the other side of the equation. So if I now plug this in to here, then I get that I derivative by time of this add minus I h0 operator time t acting on the psi at time t in the interaction picture is the same as the Hamiltonian. But then think about that in this picture we said that the Hamiltonian can be factorized into two parts, the h0 plus the h prime operators acting on the psi s, which we now again discuss that this is the same as the exponential of minus I h0 operator at time t acting on the psi at time t in the interaction picture. So after I execute this derivation here, that means that the h0 comes down, and then I will have the same exponentials, and the h0s will cancel, right? Because there is an h0 from here, there is an h0 from here, then both of them are multiplied with this exponential and the state. So those are just cancelled, but we are still left with the hi. So that the derivative of the state here is going to be the same, I dt of the psi in the interaction picture, right? What we had here is the same as the interacting part of the Hamiltonian in the interaction picture, so it depends on the time, times the psi at the interaction picture. So this doesn't sound very surprising, right? That in the interaction picture, the changes in the state are described by the interacting part of the Hamiltonian. In order to solve this equation, we use the so-called Dyson equation. So 6.3 is the Dyson equation. You probably have heard of Dyson, like he's kind of famous in the popular media. Like there are these Dyson spheres that you put some huge objects around the sun, and you just absorb all the energy from the sun and so on. Dyson civilizations are also cool stuff. So Dyson solved essentially this equation that we get to in a second ago, that derivative of the psi in the interaction picture is the same as the interacting part of the Hamiltonian in the interaction picture, which depends on the time, times the psi in the interaction picture. So what he was using is, again, this u time evolution operator. So if we get the state at t time, we can use this operator. So the psi at t time in the interaction picture is something which you can get using the u operator, which is acting to the right. So it moves the state from the t0 time into the t time. So if I plug this back here, then what I get is an equation for, so these two things together lead to the equation of I d of acting on the u operator is the same as the h I prime operator acting on the u. So this would be easy to solve if these were not matrices. So if h and u are functions, then it's super easy to solve it. That would mean that the u function is the same as the t0, that was our definition for the time evolution operator, is an exponential of, I am actually going to write it like this, exponential of minus I, the integral, whatever this function hi prime was at some t prime time integrated by this t prime variable. But these are not functions, these are operators. So that leads to some issue that h hat and u are matrices. And with the matrices, that was kind of the whole point of quantum mechanics, that you cannot just commute matrices as you wish. The ordering could matter. And here we don't know what is the ordering, what should be the ordering. So let's just take a step back and think about again what we really mean on the exponential of an operator. So what we really mean on an exponential, on a function of an operator, is really the Taylor series of that function. So the exponential of this minus I integral from this t0 to t time of the interacting part of the Hamiltonian operator in the interaction picture, and we take the integral by dt. So this we understand by doing the Taylor expansion here. So Taylor expansion, and that leads us to 1, and then whatever was in the body of the function minus I integral of t0 to t of the interacting part of the interaction picture of the Hamiltonian at t prime time integrated by this dt prime parameter. And then we have the minus I squared over 2 and the square of this h prime, and then we say dt prime squared. And of course this also goes from t0 to t. So this is just the exponential. This is what we have here, and then we want to do the derivative of this. and we do that with respect to t, we will have problems with the quadratic term. As if you take, like this part, if I take the derivative of that part, that will lead to diff of quadratic term is, I have a 1/2, so minus 1/2 of the integral of hi prime hat at t prime dt prime, and then we have the interaction picture, interacting part of the Hamiltonian at time t, minus 1/2 the other part. So then we just write down the interacting part of the interaction picture of the Hamiltonian at time t, and we have the integral for di prime h at t prime time dt prime. I really just did f times g derivative is the same as f derivative g plus g derivative f. So we are kind of happy with the second term, this, because it has the form of hi prime hat t and the u, which is the right hand side of the equation that we want to solve here. But then the first term has the age on the right side instead of the left side. So these are operators, and we just cannot just say that, oh, let's just move this guy, right? This cannot really go here. It cannot go there because in matrices or operators, age I prime hat t prime commuted with age I prime hat at t is not zero. So the solution from Dyson came in the idea of the so-called time ordering operators. Time ordering t operator. So not so surprisingly, it orders time. If I apply this t on the operators, let's just call them O1, which is at t1 time, and then the operator which is at operator 2, which is at t2 time, then the result of this is going to be O1, t1, O2, t2, if the t2, t1 is more than t2, so t1 is later, and it is the other way around, O2, t2, O1, t1, if the t1 is before the t2. So it just puts the operator that happens earlier to the left. So with this, we can finally announce the Dyson equation. So the Dyson equation says that the u at which is moving from t0 time to t time operator is the same as the timed ordered exponential of this minus I integral from t0 to t of the interacting part of the Hamiltonian in the interaction picture at t prime time dt is the integration measure. So this is really the Dyson equation, and it looks kind of abstract. So what we usually just use instead is the expanded form. So that's again the u at t0 operator is the same as 1 minus I integral h prime I from t0 to t, and we have the variable as t prime, and that's what the variable by which we do the integration, plus we have the minus I squared and the integral for dt prime, and then the integral for the dt prime prime of the h I prime t dt in the time t prime, and then we have the h I prime hat at the t prime prime, and so on. So we need to have the integral boundaries. We move from the t0 time to t prime time. That's the derivation or the integration by the t prime prime. So in that, after that, we just have a variable which is the t prime. So that is now going to get evaluated from t0 to t. So this is now an iterative equation. It describes the time evolution of a state, since this was really the missing piece of the theory of the scattering. And so now we can calculate scattering amplitudes for a design precision. And that's very important in physics, is that uh, you can just do approximations. You can say that, oh, I don't care about the next term here, and or I do care about the next term here. So whenever people do calculations, there you see things like saying that, oh, this is for leading order, and then it is for next to leading order, and then you have the next to leading order, and so on. You could go to, at this point they put numbers, so, and 3LO is the next to leading order, and so on, and it just means how much things I add here. So this was the leading order, this is the next to leading order, and then in the plus plus you have anything which is higher. Next topic to discuss is the Wick theorem. 6.4 is Wick's theorem. Wick's theorem comes in handy because sometimes the time ordering is actually very difficult. So it is useful for us because in the end, as we discussed earlier, that all the quantum fields are built up from the vacuum. And that means that we will have to have sandwiching with the vacuum state of all of these operators. So we will have to calculate the so-called vacuum expectation value. Vacuum expectation value. VEV for short. So an example is that I have to sandwich the t, the time ordering of some operators A, B, C up to Z with the vacuum state. So all these are operators. So we want to figure out what is the value of this thing. And so what comes handy now is the so-called normal ordering. So the normal ordering is denoted with an N, and the normal ordering puts the annihilation operators on the right and the creation operators to the left. Creation op goes to the left and the annihilation op goes to the right. That means that the annihilation operator will act to the right, but on the right we have the vacuum. And so this will lead to 0. So it would be nice to have a transformation between the time ordering and the normal ordering. So for this, let's build up an operator A and B so that they have the form of the annihilation plus the creation operator. So A, which is an operator, but I'm not going to put the hat on because all of these are going to be operators, is the A plus plus A minus, and we have B, which has B plus plus B minus parts. So if I look at the product of these two, A times B is the same as A plus plus A minus multiplied with the B plus plus B minus will lead to A plus B plus plus A minus B plus plus A plus B minus plus the A minus B minus. So if I apply the n normal ordering operator to this, I get AB, and that's the same as A plus B plus plus. Now this is going to be different, right? Because I have to swap these two, so that's going to be B plus A minus plus A plus B minus. That's fine. Plus the A minus B minus. So the difference between the two is just this term. So if I take the AB minus the normal ordering of this AB, that's the same as the A minus B plus minus the B plus A minus. And that's the definition of the commutator, right? So this is A minus B plus commuted with each other. So let's now give this A and B some space-time coordinates. So let's say that the A goes with X space-time and the B goes with the Y space-time coordinates. So if I apply the T time ordering operator on this A, X, and B, Y, that will be A, X, B, Y if the time part, the x0, is higher than the y0, and it will be the other way around, the y, a, x, if the x0 is less than the y0. And then the difference is between the time ordering and the normal ordering, so the t of a, which is at x, b, y, minus the normal ordering of a at x and b y, doesn't really matter for this, is going to be the a minus at x, b plus y if x0 is bigger than y0, and then it's going to be the other way around. b minus y a x plus if x0 is less than y0. And so now comes an important statement that the whole point of this normal ordering was that when you do the vacuum expectation value with those, they will give 0. So the only non-zero parts are coming from the time ordering. The vacuum, I think the t of the a x b y acting on the vacuum is this thing plus these things, but these things give a 0 contribution, so we could just include that is the same as the vacuum of the a minus at x point b plus at x y point acting on the vacuum. X0 was higher than y0, and again we have sandwiching the b minus y and a plus x sandwiching between the vacuum. X0 is less than y0. So this was kind of general, but if the A and the B operators, well, let me put it on now, is the same as the phi operator, then this thing is called the Feynman propagator. And that really just means that a particle is moving in space-time. All this seems useful, and so let's just give it a name and a notion. So this is called the contraction. Contraction of two operators A and B is denoted as this thing, and that just means what we were discussing now is the time ordering of this A and B operators minus the normal ordering of this A and B operators. So if you want to have the general Wick theorem, is that the time ordering of some A, B, C, Z operators is the same as the normal ordering of A, B, C up to Z operators and all possible contractions of A, B, C up to Z, where the contraction is this thing. Essentially we move this to the left side. There is a more intuitive picture behind all of this, and that's going to be the topic of the Feynman diagrams. So 6.5 is Feynman diagram. We will discuss the topic of the Feynman diagram through the example of the phi-4 theory. So let's recap that first. 6.5.1 is the recap of phi to the 4 theory. So you probably remember that the Lagrangian of this theory was the 1/2, the derivative of the phi, is the kinetic term, squared, minus 1/2, m squared, phi squared was the massive term, and we had this lambda over 4 factorial of the phi to the 4, which was the reason why we call this the phi 4 theory. So let's apply canonical quantization on this. Canonical quantization leads to the Hamiltonians. So that has two parts. We have the free part, the H0, an operator, which is 1/2 times the time derivative of the phi operator squared plus the nabla of the phi squared plus the m squared phi squared, and all of these are operators now. And we also have the interacting part of the Hamiltonian, which we denote with the prime, and that is just the lambda over 4 factorial of the phi to the 4, changes that now this is an operator. So next thing to do is to calculate the scattering amplitude. 6.5.2 is the calc of the scattering amplitude. This was this A, scriptic A, and we remember that we were saying that that is the out state and the in state, which corresponds to a given momentum. So let's call this momentum P and this momentum Q. And when we use the S matrix, we essentially build this whole thing up from the vacuum. So we had the normalization, some normalization factor. I guess that should be some n like this, so that you don't think this is the normal ordering. And the point is that we sandwich the creation of the particle with q momentum, it's an operator, and then we have the collision itself, the S matrix, S operator, and we also create the P, the particle with momentum P from the vacuum on the right. And actually this N is going to be coming from the relativistic formalism, so that we have 2 pi on the third, and we have the square root of 2e corresponding to the momentum. We have the 2e, which corresponds to the q momentum, and we have what we just wrote down here, the 0 a q operator s a p operator dagger acting on the 0. You remember that we have seen things in the denominator, which was the inverse of this. We had a 2 pi factor on the 3 halves, and this is also the inverse of this. So the next step is that we are going to use the Dyson formula. 6.5.3 is the Dyson formula applied. So we said that the S matrix is the same as the T time ordering of the exponential of this minus I integral of this 4-dimensional space of the interacting part of the Hamiltonian at this space-time. And we also said that it's not really easy to deal with the exponential, so we will instead do the Taylor expansion of this, which starts at a 1. Well, first, actually, I should still have the time ordering included. So the time ordering of the 1 minus I integral of this dx of the Hamiltonian prime x plus minus I squared over 2 of the integration of dy 4, and let's call the next parameter the w for of the Hamiltonian, interacting part of the Hamiltonian at y, and the interacting part of Hamiltonian in w. This is operator, this is an operator, this was an operator, and so on. So plus dot dot dot. So this is now next to leading order calculation. Okay, so now let's just plug in that the h prime was this lambda over 4 factorial 5 to the 4. So if I plug that in, I get that still have the time ordering of 1 minus I lambda 4 factorial, and then I need to do the integral, the 4-dimensional integral of this phi field to the 4th power plus the minus I squared over 2 and the lambda over 4 factorial squared, and the integral for the y 4 factorial to the 4th and the dw to the 4th of phi to the 4th operator at y and phi to the 4th of w, and so on in other terms. As a next step, let's plug this back to the amplitude. 6.5.4 was plugged it back. So the amplitude, the A, is the same as this 2 pi on the 3rd factor, the square root of the 2e corresponding to the q, the square root of the 2e corresponding to the p momentum, multiplied with the time ordering of 0 aq operator ap operator dagger acting on the 0. So this is now I plugged in the 1, right? And then I plug in the first term, I lambda 4 factorial of the integral of this for the spacetime, 0 a q phi operator at x and to the 4th power, and ap operator dagger on the 0 plus the minus I squared over 2 the lambda 4 factorial squared, and the integral for dy for the omega or w acting on or multiplied with the sandwiching of the vacuum a q phi in y. This is an operator, this is an operator, this is on the fourth power, and then we have the phi in the W, the fourth power, and we have a p dagger operator acting to the vacuum from the right, and so on. It's a big equation. We have different powers of lambda, and we can label the amplitude according to that. In the next step, we will use the Wick theorem 6.5.5, use Wick's theorem. We have terms like 0, AQ, phi, x, phi, x, phi, x, and phi x, and a, b, dagger acting on the 0 operators or these. So we can contract these two ways. In the first way, if we contract the creation operator with the annihilation operator, then that means that the field operators are going to be contracted with the other field operators. And the other method is that we would do is that the creation operator is contracted with the field operator, and then the annihilation operator is contracted with the field operator, and the field operator is contracted with the rest of the field operators. So then, let's discuss these cases. Let's say that we do the contraction of the phi at x with the phi at y. That will be 0, vacuum, the time ordering of phi y, phi x acting on the vacuum. So that's what we called the free propagator. I'm going to call it G for reasons that are a bit mathematical. It's called the green function. And so this is a free propagator, and it is propagating things from the x to the y. It is the free propagator. It moves an object from one point in space-time to another point in space-time. We can then contract field operator at x point with a creation operator. That will be 1 over 2 pi 3 over 2 power 1 over the square root of this 2e, and it was the particle with p momentum, so this is EP, and we have this ad minus ipx. Then we do the same thing with the annihilation operator. So we have a q operator with the phi at x contracted. That leads to the same factors. The p becomes a q, and the exponential term will be a plus ipx. And then the last thing is that we can contract the AQ with the AP dagger. That leads to a three-dimensional Dirac delta, which is the Q minus P vectors. So this is the Dirac delta. Only non-zero if the Q and the P are the same. So far we haven't really dealt with diagrams, so let's do that. So 6.5.6 is representing with diagrams. Okay, so when we draw a diagram, the rules are the following. We draw an interaction vertex and label them with the space-time coordinates. So with the phi for theory, we have 4 lines, because we have phi 4. Each of them are labeled with the phi, and we have a vertex, which we call, let's call it z. And so z has the contribution of minus I and the coupling constant. Then, this was for the vertices. Then we make contractions between the initial states and the field. Will be kind of the concept that we have now, this 4 things. This was all the phi earlier, and we try to connect to that a line which is coming from the AP dagger creation operator. So what happens with this is that we connect this line now to the vertex. So this here is the situation when we do the phi at x with the AP dagger operator, and this is contracted. Then when we do contraction between two fields, that is the situation that now we have, this part, and now we have the field phi here and the other field phi here, and we want to contract those. So that leads to a loop. We have this incoming thing, we have the vertex, and we have a loop. So this is the situation when we have the phi contracted with the phi. And then the only thing which is left is when we are contracting a final state with a field. So now we have the situation, and we have an AP operator here, or could be different momentum, could be AQ. So AQ is now contracted with this, will lead to this situation. So this was the situation when the AQ and the phi were contracted. So whatever we have seen in the past now could be represented with these diagrams. There are many things that we could actually do. This is not the only option that we could do. This was just really the way that we showed in the first example. We could also do things that we have more loops. So for example, this is also an option. So this is called this is a disconnected diagram, and it will have no contribution as we will see. So, but it's still a possibility. This is this connected diagram, and this is a connected diagram, and this thing was here a loop. Let's now speak about the rules for the 5-4 theory in momentum space. 6.5.7 is the rules for 5 to the 4 in momentum space. So each of these parts of the diagrams have a contributing factor. So we could say that we have the vertex here. That's the same as writing minus I lambda, or whatever the coupling constant is. Then we have a propagator, so something like this is the same as writing I, and if this part has q momentum, then this is going to be q squared minus m squared, and there is this IE where the epsilon, is a small parameter. And then you have the ending point, something like that. That's just contribution of 1, or the initial points have contribution of 1 as well. So the number of loops determine the ordering. We discussed earlier that when you go to higher orders in the Taylor series, that will lead to more Feynman diagrams. So we could just do what we have discussed earlier as an example again, that we have one loop. This is a first order diagram. So if we want to describe this situation, we need to first we need to label things. So that's called that we have P incoming momentum, and we have K momentum in here, and then we have let's say Q momentum up here. And if then the diagram for this is going to have all these factors of 2 pi to the 4, the 4-dimensional delta function to conserve momentum, q minus p, that has to be the same. Then we have I lambda over 2, and the integral for the loop. We also have to integrate out the unconstrained momentum. So k to the 4 over the 2 pi, the fourth power, and now we have what we had earlier, the propagator is going to be for the k, so that's I over the k squared minus m squared plus I epsilon. Or we could have a diagram where we have 2 loops. So let's do this. So this is P, let's call this K1. This is P again, and we have K2 here, and let's call the final to be Q. So if you want to describe this, we again have the 2 pi factor, 2 pi for the delta function for q minus p. Then we have now 2 loops, so this is a second order diagram. So that means that we have minus I lambda over 2 squared, and then we have the integral for the 2 loops, the k1 four-dimensional integral, 2 pi to the 4th power. We have the dk integral for the dk2 four-dimensional integral, 2 pi to the 4th. And then we multiply this with 3 propagators. I have I k1 squared minus m squared plus I epsilon multiplied with the I p squared minus m squared plus I epsilon multiplied with the I times the k2 squared minus m squared plus I epsilon. And let's do one more example, which is again a second order diagram, but now instead what we do is that let's say that we have an incoming p momentum which then goes in a loop like this. It goes out like that. So the outgoing momentum is still q. Let's say we have k1 here and k2 here. So then this line will have p minus k1 minus k2 momentum. So the contribution, or what we could write as for the amplitude, is that this is 2 pi to the 4, the four-dimensional Dirac delta between the q and the p, since the k and the rest are virtual particles and they don't need to conserve energy and momentum. We have the minus I lambda squared over 6, where that's a 6 because there is a contribution for symmetry factors, which I didn't mention so far, but there are certain symmetry factors which we need to include. Maybe it's less interesting or important for now. So the k1 to the 4th power 2 pi over the 4th power dk2 2 pi to the 4th power. That's our second integral, four-dimensional integral of, again, we have these propagators, I k1 minus m squared plus I epsilon, and we have the k2 squared minus m squared plus I epsilon, and we have the last one, which was the p minus k1 minus k2 squared minus m squared plus I epsilon. So whenever we just see certain diagrams, we can immediately write down how the amplitude would look like. As a next step, I would like to discuss rules for the fermions. Let's say from QED or in general. So whenever we have the propagator like this, carrying momentum p, then the corresponding factor will be I over, and we had the momentum here earlier, p squared and minus m squared plus I e is what we had earlier. So here it's actually going to be the slashed version of the p, and we could actually multiply this with the p slash plus m and get that the same thing is true plus p slash plus m divided with the p squared minus m squared plus IE epsilon. So now it has a similar form as we have seen above, but the new thing is that this is going to be now a matrix, right? Because we slash it together, the form momentum, we slash it together with the gamma matrix, and by that we get a matrix. When we have an incoming particle with p momenta and spin s, that's going to be described with the us, which is depending on the p function that we discussed in the last video. When we have an incoming antifermion with momentum p, which we will denote as the line goes like this, and then we say that the p goes up. So this is a notion for an antifermion, and this is a notion that it has p momentum, which is going up. That's going to be the v bar of s for the p. Like this is ingoing, this is again ingoing. So when we have outgoing particles or outgoing lines, then like this is going to be an outgoing fermion. So for that, there is contribution of u bar s p, and we can have an outgoing antifermion. I need to swap the arrow, and to show that the momentum is showing up is going to be the vs. And let's give an example where we have an electron-electron scattering. So let's say that we have an electron coming in like this, it's a particle, and like that. This is our diagram. So it will have contributions of I, the minus I actually, minus IG is the coupling constant contribution for the vertex, and then if we have P momentum here, and this is going to be USP, we have U anti USP here, and let's say that we have K prime momentum here and K momentum here. So this is going to be described with the US K prime, and this is going to be the U S and K. And actually, the spin doesn't have to be the same, so we could call these things with a different letter. So let's denote the spin with R in this second case. And there is one more thing which you need to label, that this momentum here, Q, is going to be the same as the difference between the P and P prime. So if we want to write down that this is the same as minus IG squared, one here, and then we have the U S P prime, the U S P, and then we have I P minus P squared minus M for the particle that's in here. as the I epsilon, and then we have the U dagger bar R K prime and the U R K. Let's now actually include the photon as well. So in this example for QED, we should have photons. So the rules for the photon. So whenever we have now a vertex again, we denote the photon with a wavy line, and then we label the index with Greek letters. So it's going to be the mu, and then we have p prime and p momentum here. So that means that the momentum carried by the photon has to be the difference between the two, p minus p. So the contribution for this vertex is the minus I, that's very similar to earlier. We have the coupling constant again, which is the charge for QED, but what's new is that we need to include the gamma matrix gamma mu for the photon, for the vertex. And then when we have the propagator, so we have just something like that. So this part is now, let's say, carries k momentum. So that's going to be described, and it's again going to be kind of similar to what we've seen earlier, the I, and then we have the k squared, and you remember we had earlier plus or minus m squared, but photon has zero mass, so that's zero, and we have the I epsilon. So what's really new is that there is going to be that this photon connects the mu vertex with the nu vertex, so there is a g mu nu indexing here. And then when we have the incoming photons, so with p momentum, that's going to be described with this polarization vector epsilon mu lambda, because this was the mu index and that carries p momentum. And then if we have it the other way around, this is an outgoing particle, so this is going to be epsilon star and nu lambda p. So this vertex is now nu, and then the lambda is the polarization index. So let's have an example with these two. We have an electron incoming, or let's call it an electron positron. Electron goes like this. That means that the positron will go like this. You should also know that the momentum goes like that. So that's p prime, and it's p here, and then we have the photon with q momentum, and then the photon emits the electron positron again, or we could now do a bit of a difference and say that it emits a muon and an antimuon, and the momentum flows this direction. That's the k prime, and here it's k momentum. So then this will be described by starting with, here we have an antiparticle, so that's going to be v bar s, let's call it prime, for the p primed particle. Then we have minus I e or q, doesn't really matter, the charge, which is the same as the coupling constant. And then we have the gamma. I didn't actually write it down, and we should also have the vertex's name, so this should be the mu vertex, and I'm sorry that the muon, let's call the muon like this. If there is a plus minus, it's a muon. If there isn't, then it's the index, and the other one should be nu. So we have the gamma matrix for the mu vertex, and then we have the USP, which is for the electron. It's a particle, so we use the US, and then we have the propagator for the photon. So that's I, G, mu, nu. It connects the mu and nu vertices, and we have Q squared plus I epsilon, and we multiply this with the what we have in the right side. So we have the anti-particle and the particle again, so that's going to be U bar R K, and we have the vertex minus I E gamma nu, and we have V R prime of K prime in the end. So this was the electron positron moving to a muon and an antimuon process. There is one more thing which I would like to show here. That's just a trick that whenever we do a summation for these u and v's, so the sum for the spin of us for a given momentum p and u bar s for the same momentum will be the same thing as the p slash plus m. So when we do the calculations later, these will be summed and will lead to a bunch of p plus p slashed matrices with the mass, and then we see that we also have this p slash in the denominator or in the numerator up here after all, after doing this transformation. So in the end, these calculations are a lot of matrix multiplications. And so essentially with this, whenever we draw anything that you can think of, you can figure out what is the description of that in the amplitude. So we could have this vacuum polarization, a photon creates an electron or in the positron, and we could write down what is the corresponding factor. But then like we could totally do more complicated things that well, there is a photon created in here or a photon created in here, and then you can really do more complicated things. You could create an electron positron pair here, and they could exchange a photon. Why not? And then as you wish, the complications could go to infinity. And whenever we observe a process, it's going to be the sum of all these amplitudes. Let's now speak about the transition matrix and the Feynman invariant amplitude. 6.6 is the transition matrix and the Feynman amplitude. So actually, these things are not really changing anything in the physics of the discuss. It's rather a change in the how we present this. So it's customary to remove the 1 from the S matrix in the beginning when we do the expansion. And so that's actually what gives rise to the transition matrix. So we say that the S is the same as BOM plus I times the T, where the T is the transition matrix. So we do this because the 1 doesn't change anything. This is just the situation without the interaction. So it doesn't really tell too much. So it's really the T which says something about the interaction. We have one other weight that we always carry on. This is the overall energy momentum conservation, and we have a delta function for showing that. So it's also often factored out to make the so-called invariant amplitude, or invariant Feynman amplitude, which is denoted with the m. So in the m, invariant amplitude is understood. So I can say this is invariant amplitude. That's the same thing when you have, let's say, two particles coming in, P1, and this is the final state, let's say, and then you have the P2 particle in the final state, and then you make the sandwiching between the initial state of these two particles, and so that will have these terms of 2 pi to the 4, which is the constant, the delta function, the four-dimensional delta function that just includes that the momentum in the final state of the first particle plus the momentum of the second particle in the final state minus the momentum of the second particle in the first initial state, and the momentum of the first particle in the initial state has to add up, and the rest is what we call the invariant amplitude. The next thing to discuss is about cross sections. 6.7 is cross sections. So finally, we reach the point where we can really calculate something that we can measure. Imagine that you shine light on a black and white object in a dark room. If the object is big, then the reflection of the photons in your eyes will be big, so you have a higher chance of seeing it. But there is another effect. The object is dark, the diffraction will be smaller. So the analogy with the colliding particles is that the area considerations are included in the so-called cross-section, and the other effect is included in the luminosity. So we call sigma the cross-section, and L is the luminosity. So this is the analogy with the area, and this is the analogy with the white black spots in this example I mentioned earlier. So when we calculate the differential cross-section, so we look at what is the cross-section per an angle space. And so if we have two particles, this is going to be the invariant variable amplitude squared over, and this is something which is specific to the two particles which have the same mass. So we have this constant 64 pi squared and the energy, the center of mass energy. So the omega was the solid angle, and the ECM is the center of mass energy, and this formula is true if we have two same mass particles. This is actually true for what happens at CERN, for example. We have two protons colliding, so their mass will be the same, and so if you calculate the cross section, this is the formula to use. We can get the cross section by integrating this differential cross section. So the cross section is the integral of what we just did here. So it is the omega integral of the d sigma d omega. And that is also the same as if we would do an integral from 0 to 2 pi and the integral from 0 to pi of the d sigma d omega. So this is just the solid diagram. Next thing to calculate is the rate of the scattering process. So the rate, let's call it R, is calculated as the multiplication of these two things, the cross-section and the luminosity. And then we can do one more thing, which is not going to be super obvious of what's happening. This is the number of events. Number of events. How many times do we see a certain thing happening? And that is going to be the integral of the rate. So if I integrate the rate by time, I get the number of events. So I could take out the sigma. That's something which is not changing over the time. And then we have the luminosity. So this R is really the luminosity here. Luminosity. And if you integrate the luminosity, you get something which we call the integrated luminosity. The last thing to discuss is about what kind of research we do at CERN and how is it connected to what we were discussing. So 6.8 is about CERN research. So I took this plot from one of the dark matter searches, I believe, from CMS. And so what we see is that we see the certain momentum, the transverse momentum of the particle plotted on the x-axis. So maybe I should start with saying that like we have a collision of two protons, and then there is from this collision event we get different kind of particles, and then we build a detector around it, and so we will measure those things. And the momentum in this axis where the particles came in is going to be, it's just nothing special. The protons have the same momentum in that direction, so that's not very interesting. What's interesting is the PT, the transverse momentum. So that's what the green thing is now perpendicular to these lines, the white lines. So we do that, and then we plot the events. So these events are exactly what we calculated earlier, that that we could now calculate based on the Lagrangians. So first, we could look at that the black points are the um, the data points. So we see that with a given momentum, we have let's say 10 events with a different momentum. We have one event per GV and so on. And then what we do is that we compare these data points to simulations. So let's say that we pick this thing. So this orange is the TT bar. So that means that the proton meets with the proton, then they create some energy or something happens here, which is complicated. So I'm just using a bulb to it, and we get a top quark out of it, and then anti-top quark charge is conserved. So this is something which we can easily do. So how many top anti-top quarks do we expect if this momentum, transverse momentum, is around 300 GeV? Well, we expect, you see, it's from 1 to 10, so 9 events. We expect 9 events. But then we actually have 10 events in data, so that is because we have a tiny bit of a second bit of W plus jets, and then we have this is this point, and then we have a lot of, or single T, not a lot of, but we have some single top in that bin. So that's what we do, and then we should sum up the simulations and look for differences. So like anything new is going to be the black points, black data points minus the sum of the simulations. And these simulations contain the standard model. And they are calculated based on what we just discussed. So, like in just to recap a bit, is that the whole story was that the rate was the same as the cross section and the integrated luminosity. And then in the cross section, we had that the sigma was proportional to the m invariant amplitude. This invariant amplitude was calculated using the Dyson equation, which included this vacuum expectation value. So it was the 0 and things in here. And then what was the most important is that we took the Hamiltonian, the interacting part of the Hamiltonian with some other parts. And then the Hamiltonian we got from the canonical quantization, which we got from the Lagrangian, and the Lagrangian comes from some symmetry considerations. But essentially, if this just means that if you have the symmetry groups, from that we can figure out the Lagrangian. From that you can figure out the interacting Hamiltonian operator, right? That was important. And during using the canonical quantization, which then leads to the invariant amplitude, which then leads to the cross section, which then leads to the rate, which then leads to these kind of plots and the possibility and hope to find something new about the universe. With this video, we have reached the end of particle physics topics. The next video will deal with macroscopic quantities and a bit of a material science. It is going to be exciting since we will build these things up from the same kind of Lagrangians that we have been discussing so far in these 6 lectures. So, see you next week.